this is the derivative method specifically. So I want to go through this problem real quick. Really, we had two of them. I think this was one problem, if I'm not, is that the one you guys got? Do you remember that one?
Yeah.
One of them was negative, one of them was positive. They were the exact same problem, right? I'm just gonna do this. I'm gonna call this A. I don't wanna make this is x of t. Amplitude A, make this minus tau, all right? And then let the period be, when it starts over again, just call the period capital T. So now we're talking about arbitrary values. It doesn't matter what those values are, really. For one of them, the width here, tau, was 1/2, and the period was 2, I believe. Right? It doesn't matter what they are. Now, if you take a look at x of t here and take one derivative, then you get this, x prime of t. From here to here, it's a constant slope. The slope is a over tau. Do you all see that? That means it just becomes a constant. The height of this is a over tau, right? Now, what happens from here to here? That's a delta function, isn't it? It went from a value of a to a value of 0 instantly. So we put a delta function there. And the weight on that delta is minus a, correct? Now, keep going. When you hit here, what happens? The period, t. Now it repeats itself. You all see this? So now you have this, and then you have this. Minus a, and this is really t minus delta of t minus capital T. The height is still a over tau. And it's going to repeat itself forever, both directions. Do you all understand that? Now we want, look at this, we're going to say, we're going to decompose this x prime into two functions. We'll call it x1 prime of t plus x2 prime of t. All right, one other thing I'm going to say before I continue down the track. When I look at this, I've said this before, you have to get your x0 value by taking 1 over t, the integral of x of t dt, from 0 to t, or over any one over a period. Correct, class? Now, you don't have to do the integration on this one. You're welcome to if you want to. We can get an equation for this line. The slope is a over tau. The weight on this is t, so it's a over tau times t plus the 0 intercept, which is minus tau. Do you agree with this? We could write an equation for the line from here to here and do the integration formally. But whenever you see triangles, right triangles, don't make it hard on yourself. What we know that this is equal to, it's 1 over t, and this is simply the area under the curve, isn't it, class? Well, what is that area? It's a times tau divided by 2. So this is simply a times tau divided by 2 for a right triangle. How many see that there? Right. This is meant to be, and I said that too many times, I don't mean to pour salt in your wounds if you missed it, but I'm trying to say I was not trying to trick you. I was going out of my way to make this dirt simple. Now, if you see that, that's x0. Now, these two functions I break out as two different series. x1 of t, prime, is going to be just this series, the a over tau box function that keeps repeating itself. I can write an exact expression for this, but this is not necessary right now. The second series is just going to be all these negative impulses, and I'll call this x2 prime of t. You all follow me on this? Now I've got two series, right? I'm going to come here and take a look at this delta function series. That's what I want, a whole bunch of delta functions. If you want an exact representation for that, I can say that x2 prime of t is equal to just the sum of delta functions with a weight of minus a, delta of t minus nt, where n goes from minus infinity to infinity. That's an exact mathematical representation of that series of delta functions. You all see it? If you want to write it, you can. It's unnecessary, though. Now I want to get the Fourier series associated with that. That means what I want to get is the summation of x2 prime, think of, well, x2 of n times e to the jn omega naught t from n equals minus infinity to infinity. And I know that x2 prime of n is equal to 1 over t, the integral of x2 prime of t times e to the minus jn omega naught t dt over a period, but I'm going to go from minus t over 2 to t over 2. You realize what I'm trying to do here is trying to get the coefficients that go in that Fourier series that represents this string of delta functions. Do y'all remember this, class? All right, what is that going to be? Well, Here, I only have one delta function between minus t over 2 and t over 2, and that's this delta function right here. So the coefficient associated with that would be x2n prime would be 1 over t, then it's the integral of minus a delta t, you can forget this infinite series, it doesn't matter, times e to the minus j n omega naught t dt. And that goes from minus t over 2 to t over 2. And what is that value going to be? What do you do if you have a delta function inside the integral, class? Find out what the value is the functions adjacent to it at the point where the delta function turns on. It turns on at 0. And therefore, e to the 0 is 1. It's minus a over t. Minus a over t. It's not got a variation with n. That's what it is for all n. Right? Now, I want to go back. What I'm really doing here is I'm saying x of t is really equal to some x1 of t plus some x2 of t, right? Now I've got x2 of n prime, but when I want to go back to get the original, I have to divide by jn omega naught because I took one derivative. Do you all remember this, class? So now I can say that my actual x2, if you wanted the series, it would be the summation, right, of that coefficient minus a over t times e to the j n omega naught t from n equals minus infinity to infinity. And that would be x2. Now x1, do you all see this, class? That's just the series for the delta function, the series of delta functions brought back to the original to the pre-derivative point, all right? Now to get this, the series associated with x1 here, I need to take another derivative, correct? I want to erase those delta functions so we can focus on it. Because we've taken care of that, we got the series ready for x2. So now, when I look at this is x1, correct, class? Now, careful on this one. There's a lot of, I know people can get sloppy. If I take another derivative, x2 double prime of t, what happens right here? Minus tau. Class? Of weight what? A over tau, delta of t plus tau, correct? Because when that argument is 0, that's where the delta function goes on, right? What about here? It's a negative a over tau weight, and it's at 0. So now you got one like this. Minus a over tau, delta of t, just t, right? And that repeats itself. But for the sake of being brief, I know my integral is only going to go from minus t over 2 to t over 2, right? So I'm not going to write a mathematical equation for that, but you all see I can do it, can't you? I mean, that's a fairly straight thing. So now for that series, that's a double prime series, and I have x2 double prime of t is still equal to the summation of x2 of n double prime times e to the j n omega naught t from n equals minus infinity to infinity. And my x2 of n double prime will be equal to the integral from 1 over t, from minus t over 2 to t over 2 of this function right here, right? So I'm going to go ahead and put it in, just to make sure you see it. I have a over tau is the weight. I have delta of t plus tau here, and it's minus delta of t here, all times e to the minus j n omega naught t dt. Do we all agree with that, class? You all see what I'm doing? I've put in the function, the derivative function inside, right? And I'm getting the Fourier series coefficient for the for the series of delta functions right here. When I get that, and it's going to be easy to do, then I divide by j n omega naught squared because I took two derivatives. All right, so this one becomes what? Well, I know I'm going to have a tau over t right here, and then I look where this one turns on is what, class? T equals minus tau, right? So I put minus tau in here, and I get e to the plus j n omega naught tau. Now I take a look at where this turns on, and it is 0, right? At 0, this becomes just 1, right? Now that's the value of the coefficients for this series, right? But to get this series, we took 2 derivatives. Remember, every time you take a derivative, you pull out a Jn omega naught, right? So we take this and divide it by Jn omega naught, and now I can say that x, I call this x, x1, I should call it x1, I'm sorry. x1, my bad. Now I can say that x1 of n, or the coefficients will be that, a over tau times t times e to the jn omega naught tau minus 1. And then I have to divide this by jn omega naught squared. Correct, class? Everybody see what I'm doing step by step? It's very straightforward if you've been listening to the lectures and paying attention. There's nothing tricky. There's no crazy integrations. These are just derivatives and making sure you divide by jn omega naught squared. Now, that means that this is going to be my x1 of t, and I'll put it right here, is equal to the summation, right? And now I'll put that in there. That's a times tau, or I mean a divided by tau over t, right? Times e to the jn omega naught tau minus 1 divided by 1 over jn omega naught squared times e to the jn omega naught t from n equals minus infinity to infinity. That's x1 and x2. When you combine these series, you're going to add the two, right? Please watch this and see this. You'll notice that the e to the jn omega naught, e to the jn omega naught t, right? That appears in both of these. So really what we can do is just take these coefficients, that coefficient plus that coefficient, and break it out separately. Do you all see that? And once you do that, you find that the series itself, and I'll put it here, the final series, x of t, is equal to a summation. And now I'll take the first coefficient, minus a over t, plus a over tau t, right? Pardon me. I gotta go ahead and, I didn't divide this by, sorry, j and omega naught. That was my mistake. I did there. That should be divided by j and omega naught. Plus a over tau t. And now I have I have e to the jn omega naught t, or e to the jn omega naught, pardon me, minus 1 divided by 1 over jn omega naught squared times e to the jn omega naught t, and that's the series where n goes from minus infinity to infinity. And all I've done is add those two constants, right? Now, the one thing that I've gone through a couple times in the lectures, actually 3 times, I believe, is when you see something like this, always convert it to either a cosine or a sine. And I'm going to do that over here to make sure everybody sees it, because this is important. You'll be doing this all the time in engineering. Here we have this, e to the j n omega naught t, or I mean omega naught, pardon me, minus 1 by itself. Do you all agree with that? Yeah?
For this one, we don't need the average value, right? Because it's a
Yeah, you
double
do.
series.
No, you have to have the average value. I didn't add in the average value. I should say n unequal to 0. I'm glad you said this, plus x0. You have to have that. It's non-zero. The average value had a value of what? What was it? It was a tau divided by 2 divided by t, correct? Right? It's the height times the width of that. It's a times tau divided by 2 divided by capital T for the average value. You have to have that average value. All right, now, and I appreciate that because I actually omitted it. Now, the thing I'm just driving at is this. whenever you see something e to the j n omega naught, either plus or minus 1, immediately think turning it into a trig function because you understand trig functions. Do you follow me on this, class? Well, for this one, we can play all sorts of games with this. This is tau right there. I'm going to pull out, what you do is take this superscript and divide it by 2. Well, this superscript here is 0, right? So 0, this would be e to the j 0, if you will. You follow me? Plus that divided by 2, you pull out e to the j n omega naught tau divided by 2. Now here, you have e to the j n omega naught tau over 2. Then you have minus e to the minus j n omega naught tau over 2. Do you all follow me? Here I've done a simple thing. I factored out a portion of that, half of the actual superscript value, in order to make this into a trig function. And I know that if I have e to the j theta minus e to the minus j theta divided by 2j, I have sine of theta, correct? Theta here would be n omega naught tau. Do you all see this? Divided by 2. All right, well, I multiply by 2j, and I can see that I can replace this by simply, this would be e to the j n omega naught tau over 2, and this is 2j times sine of n omega naught tau divided by 2. Now that makes the calculation easier to see. Now, you're not dealing with e to the j some angle plus 1, where you have to add and look at them vectorially. Here it's a sine, right? And we know that omega naught here is 2 pi over t, correct? Then, when you look at this, I believe tau was 1/2 and t was 2, right? Correct, class? Yeah. So it's really capital T divided by 4. Do you follow me, everybody? If t is 2 and tau is 1/2, that's 1/4 of t. Do you all see that? So you can put it in here. You can go ahead and say that what I've got here is tau is equal to capital T over 2, and therefore omega naught tau right there is really going to be equal to pi, oh, I'm sorry, tau over 4, pi over 2. You all see that? Now you put that in there and you get pi over 4. You all see? So this becomes pi over 4. And I wanted the value of, that was the last part, were 3 points. I wanted the value of this coefficient right here, this part of it, I wanted the value at n equal 8, didn't I? All right, well look here, what is it? When n is equal to 8, 8 over 4 is 2. The sine of 2 pi is 0, same thing as the sine of 0, so it was 0. It was meant to be something you saw. Remember when you did this, when you did the MATLAB project, you saw, if you actually printed the coefficients, you saw every 8th coefficient go to 0, I believe it was. All right, and that's where it comes from. Now, if you didn't mess around with the MATLAB project, you probably didn't see some of the things, but that was what it was meant to show you. You turn it into either a sine or a cosine. It makes the evaluation so much easier. All right, that's how that problem was supposed to go. And that coefficient right there, the whole thing is, this becomes 0, so the final coefficient was just minus a over t times omega naught's 2 pi over t, so it's minus a over n times, in this case, 2 pi right here. You put in n equal 8, and that would be it. Are you with me on that? This one goes away completely. Got it on that, class? Now, you probably struggled with the evaluation if you didn't do that trick. And I'm gonna give you some leeway on that one, all right? But that's how you do this problem. Please, from now on, make sure you know how to do these things, because they're gonna come up over and over again. Are there any questions about this? Yeah.
Could you go over the sign transformation?
Do you know Euler's?
Yes.
Well, you know, for Euler's identity, it's e to the j theta minus e to the minus j theta over 2j is sine, right?
Okay.
So the only thing I did is multiply by 2j on both sides to get that. And theta was the argument here. It was n omega naught tau over 2. You gotta know cosine, right? And you have to know what e to the j theta is. That's cosine theta plus j sine theta. Now you have to know these without any kind of hesitation. You have to know them like V equals IR. And I can't overstate that, because you're gonna, I mean, the stuff you're getting into is real thickly, or it's intensive mathematically. Those type of things, Euler's, stuff like that should be second nature. I'm just telling you, that's where we're going. But now we're gonna use this stuff today to do what is real engineering, and that is actually figure out how a circuit or any system responds to an input that is periodic but not a simple sine wave. For instance, this waveform. The real way you appreciate this is you do this, and you do some homework with MATLAB so you can understand what's going on. MATLAB is something that does have a learning curve, but once you learn it, you'll be thankful you did, because it's such a powerful language. Something else about MATLAB. How many know that they have toolboxes in MATLAB? In other words, they have pre-canned functions that'll do anything you want. You want crazy Bessel functions, if you want Maclaurin series expansions, pick something you want, it does it. Mathematica does it too, and to some extent MathCAD does it. MATLAB, though, was designed specifically for prototyping. That's the reason it's so good. They were very first code before you get into a more basic, or more, I'd say, cryptic language like C, you do it in MATLAB. At least most people do it in MATLAB or Python these days. So now, here's the deal. We're gonna take any periodic signal that comes in, and we have a system here. Now the system has a transfer function h of t. The output technically would be y of t, would be h of t convolved with x of t. But this is especially true if it's periodic. That's the normal way we think of it, right? When it's a periodic function, we take x of t and we break it into its Fourier series, where we have, let me do n unequal to 0 here. We break it up and we say it's x of n e to the j n omega naught t right here, and put a plus x0 here. So we're going to take that series, if it's periodic, and break it up to the Fourier series, right? Now, we take this series and we turn it into the single-sided cosine series. I want you to see every step in the way. So now when I take x of t and turn it into a series, a cosine series, I get x of t equals x0 plus the summation of n equals 1 to infinity of 2 times the magnitude of x of n times the cosine of n omega naught t plus the phase angle on x of n. That's really what's going to go in there. You follow me? That's what we're going to shove into this thing. Everybody got that? I'm going to erase this other one, but I wanted you to see that this leads to that with that little trick I showed you. So I'm going to get rid of this completely. Now, look at this for a second. We have a whole bunch of terms that have a specific frequency with a specific magnitude. When I have n equals 1, it's the fundamental. The frequency is omega naught, right? You all see that? N equals 2 is 2 omega naught. The weight out here would be x1, x2, respectively. If we took this and put it into the phasor domain, this is what you're used to doing, right? If you had 10 cosine of omega naught t plus 30 degrees, and you were doing a circuits problem, you would have a 10 at an angle of 30 degrees. Do you all remember doing it? It's critical you see the linkage. So I'm going to take this and I'm going to put it in the phasor form. So now I'm going to have x, and I'll put x phasor, just equal to some x naught plus the summation, right here, of 2 times magnitude of x of n, right here. And it's going to be at that angle, so it's going to be e to the j, simply the angle of x of n. N equals 1 to infinity. And you notice what I did. I got rid of the cosine n omega naught t, and I put x of n, the weight of it, and the phase angle. Do you all see this right here? Those are phasor terms, magnitude and angle. No longer do I write the cosine of omega naught t out. Follow me? Now what goes in here? Well, you remember when you analyze circuits, they were at a given frequency, omega naught, right? And what did you use omega naught for? To get the impedance of the inductor, J, it's really, what, J omega L, right? And the impedance of the capacitor, 1 over J omega C, correct? And then you did circuit analysis as if you had resistors that had complex values. Do you all remember that? That's the same thing that happens here. Now when we have a transfer function, this will be h of n omega naught. it's not gonna be h of omega, because it's not gonna have just one omega, it'll be omega naught, 2 omega naught, 3 omega naught, follow me? And that transfer function has a magnitude and an angle. So I can say my h of n omega naught really has a magnitude of h of n omega naught. And it has a phase angle, e to the j phase angle of h of n omega naught. Do y'all agree with that? And that's true with any transfer function. Transfer function is always output value over input value, right? It's the ratio of output to input, whatever they are. That's what it always is, a transfer function. Now, out here, what we find is, how do you do it with phasors? Well, if I wanted the output of this, I'm gonna put it up here. My output is y. I want y here, but it isn't gonna be for a single frequency, it's gonna be for all frequencies. So y right here, let me do it this way, of n omega naught equals, well, what is it gonna be equal? Let's go here. When n is 0, it's just x0 times h0, isn't it? So it'd be x0 times h0 at a phase angle of 0, and it'd be e to the j phase angle of h of 0. That's almost always 0, by the way. Almost always. It's a DC term. You can't have a phase. Well, I can think about, yeah, you could get a -1 in there, all right. So, yeah, you could have a minus pi phase, but generally speaking, it's not. Then you're going to have what? Plus the summation of n equals 1 to infinity. And here you've got to be careful. You're going to have 2 times the magnitude of x of n. That's the weight right here. It would be the value on the cosine, right? It's at a frequency n omega naught, right? There's a phase angle in there. It's e to the j phase angle of x of n. Now that's multiplied by what? Magnitude of h of n omega naught, e to the j phase of h of n omega naught. And that is the term-by-term output of the actual system in the phasor domain. You all see this. We take the input, just do one at a term. Suppose we had just 2 volts at cosine of 377t plus 30 degrees, right? That's 2 at an angle of 30 degrees, right? You want the output, you take 2 at an angle of 30 degrees times the transfer function, h, right? Whatever it is, it's got real and imaginary, and you get the output value, right? You all remember doing that in circuits, correct, class? Now, that's for only one frequency. We got to do it for all possible, and that's why we have this. Now, that's still in the phasor domain, though. But when we go to the time domain, how do you take anything, magnitude, if I had, say, 10 at an angle of 15 degrees, volts, and I wanted to go back to the time domain, what do? We take the magnitude here and put it out in front. Then we write, now we reintroduce the cosine of omega naught t plus the phase angle 15 degrees. Correct, class? That's in the, this is the observable domain. We can see that. We can measure that with a voltage meter, right? This is the non-observable. That is something that's used for circuit analysis purposes. If you had Irwin, he probably really did a good job bringing that out. That we're analyzing in the phasor domain, but in the things observable, measurable in the time domain. That's a big difference. Now when we take this to the time domain, and this is what we have to do correctly, now I can say that y of t will be equal to, that's dc x naught times h of 0. And you might as well forget about the phase because it's almost always 1. It's just the transfer function value. If the transfer function's got a negative sign to it, go ahead and put it in there. But that's a constant. Then it's plus the summation here, n equals 1 to infinity. Now we do 2, and we group the magnitudes times magnitude of x of n, magnitude of h of n omega naught here. Then what we do here, that's our phase angle total. It's this angle plus this angle. So now we put the cosine of n omega naught t in here, plus the phase angle of x of n, plus the phase angle of h of n omega naught. And that's the output. It could be in volts or it could be in amps. But now if we have a system transfer function, we have an input that's periodic, and we break it into the Fourier series. Now we can get the output in terms of a semi-infinite series. By the way, just for the purposes of discussion and practicality, usually here, you might take maybe 100 terms, usually much under 50, to see what the output looks like. That's the majority of the information is in the first 50 terms. But each of these terms, if you remember doing this with MATLAB, when you started adding more and more terms to your series, it got cleaner and cleaner. Less ripple, less, except right at that discontinuity. You always get a 9% overshoot. It's 8.98, something like that, percent overshoot. And you can't get rid of that. Are you with me, class? All right, now this is basically, how many of you SPICE, P-SPICE, stuff like this, LT-SPICE? How many have again? Don't you have to do a SPICE project in the lab? Everybody here has, what lab is that? The circuits lab?
Digitron, we have to use LT SPICE.
LT SPICE?
Yeah.
Well, that's what LT SPICE is basically doing. Only they have advanced things so they can get rid of that overshoot and stuff like this. They have ways of signal processing to eliminate spurious stuff that's not really there. How about we do a problem and you see all 9 yards of this, all right? That way you'll have an appreciation for this. Make sure you keep up with the MATLAB work too, that I'm gonna give you. You have Dr. New. Dr. New is going to be asking you to do LT SPICE simulations. Does he ask you to do Python or MATLAB simulations? Not yet. Well, you're going to do some more MATLAB in here as extra credit. So let's start by doing this. We're going to come up with a simple problem of a periodic signal, get the Fourier series representation to it, right? And then see what the output of a circuit is for that input Fourier series. Let's do a really common one. How about this? This is really common. That's ye old square wave. All right? X of t being a square wave. Let's make this tau, and let's make this t, and it repeats itself, so it goes on forever. Got me? That's a square wave. No matter what you do to it, it's still a square wave. All right, now, we need the Fourier series for this, right? We're going to take one derivative, and I better make this a here. I take one derivative of that, what do I get? Well, I get this going up to a at t equals 0. Then at tau, it goes minus a, right? And then it repeats itself. Now that's x prime of t. And I'm just trying to give you an idea. It's a bed of nails, top and bottom. There's two of them. Professor said that to me. It stuck with me all through. The way it was a picture in my mind. Yeah, bed of nails, I can hear you. That makes sense. It looks like that. It's a whole bunch of spikes. I want the Fourier series for this. I want the coefficients, and then I'm going to take that coefficient and divide by j and omega naught. Got me on this? So for this one, I know that my x prime of t is equal to a summation. This part you don't need to write down. I write this down just for completeness, so in your mind you're thinking. I know this is the xn of prime I'm calculating right here, e to the j n omega naught t. Xn of prime right here is equal to 1 over the period times the integral. I'm going to go from t over 2 to t over 2. In other words, my window of integration is going to be just focusing on these two. All right, you all see that? Just those two. So when I do that, I'll put in the value for that. It's really going to be a is the weight on that. Delta of t, right? Minus delta of t minus tau. That's it, times e to the minus j n omega naught t dt.
Wait, which one are you focusing on? The one in front of it?
Oh, I'm sorry. I got it circled wrong, my bad. I'm going to focus on just these two, my bad. Those two, one at 0, one at tau. I could get the one back here, but it's got to be over a period, so these two. You all follow me. I'm not doing this for the entire series. It's just over a period, and I always slide that window of integration, so I'm not on the edges of any kind of a discontinuity or in this case, a delta function. When I do this, I see my x of n prime, right, is equal to 1 over the period times a, And then I have 1 right here minus e to the minus j n omega naught tau. And please check and make sure you see that that in fact would be the coefficient. You all see if I do that integration, necessarily that is the coefficient. Are you with me, class? Everybody got that? Now, if that is the coefficient of x of n prime, I want to get my x of n, so divide by 1 over j n omega naught, right? And now I have x of n, don't I? There's one more thing I'm going to do. Anybody see it? To help get it,
Spoilers.
turn it into a trig function, right? Remember what I told you, this is really e to the j0, this is e to the minus j n omega naught tau, right? Add them up, you get e to the minus j n omega naught tau, divide by 2, pull that thing out in front. So now I'm gonna go ahead and do that. And I have this as a times e to the minus j n omega naught tau divided by 2, divided by t times j n omega naught. And I just put that out in front. And now I have what's left is e to the plus j n omega naught right here, minus e over 2, tau over 2, minus e to the j n omega naught tau over 2. Please take a look at that and see that in fact, when you tear that out of there, you get this. You all see it? Class, take a good look. Can you see it in the back there? Can you read it from where you're, I'm always concerned about people in the back because you're looking through heads a lot of times and it's hard to see when you're low. Okay? Now, what's my next step based on the prior problem? How many see we're going to turn it into a sign? Can you show me? You all see that I'm going to put 2j times the sign of the argument in the exponential there. You all see that, class? So I'm going to do it. Do you mind if I just erase? Well, I'll let you catch up with your writing. And I'll do it. I'm going to economize board space if I can. Anybody go to the basketball game? Well, Pearl's going to have to put a cardiac ward in instead because it's not going well for a lot of people, including me.
Oh.
They're down by what, 17, and they came back? I mean, psychiatrists, cardiologists, everybody. That thing's crazy, wow. All right, so now replace that with 2j times the sine of n omega naught tau over 2. I've just done that to make my life a little more easy to deal with. I can deal with that real easy. Got me on this, class? Now we go ahead and we say, well, that's the input to a circuit. So now I'm going to find a circuit. I'm going to make one up. And if you've got a preference, tell me, and I'll put your circuit up here. And it doesn't matter. So I'm going to say this is the input right here. This is my x of t. And my output is going to come from this circuit. I'm going to have a resistor R, a capacitor C. And I want to take the voltage across the capacitor. Here's my output, y of t. Follow me? Now we need the transfer function of this. Now hear me on this. Think about it. If you go into the frequency domain in Dave Irwin's class or whoever you had for circuits, R is still R, isn't it? But what happens? C is replaced by 1 over J C, right? J, 1 over J omega naught C. But in this case, it's not omega naught, it's n omega naught. Got me on that? Now, this is replaced by an impedance of 1 over J n omega naught C. Okay? We're going to get y of t in a second. You all see this? That's input output, right? Now what is the ratio? I mean, what's input over output? When I want my h of n omega naught, I really want v out of n omega naught over v in of n omega naught, correct? That's the ratio. You all see how this is a series circuit, and this is simple voltage division. It's the impedance of this element over the sum of this plus this. Do you all see that? I'm going to write it down. So this is going to be R over R plus J, or plus 1 over J n omega naught times J n omega naught C. Right? And that's the transfer function. I want to put this, do y'all agree with that? I want to put this in a form of something that probably I understand a little bit better. So what I'm going to do is multiply top and bottom by j n omega naught c. I'm not saying you have to do it this way. So I have j n omega naught c times r over really 1 plus j n omega naught c times r.
Question,
Oh, hold on. Wait a second.
the voltage division needs to be across the capacity.
Yeah, this is going to be, you're right, absolutely right. Let's see, this should be 1 over j n omega naught c. My bad. So when I multiply first by j n omega naught c, then I get 1 over, and this is going to be 1 plus j n omega naught c times r. I'm sorry about that. You're absolutely right. You all see what I'm talking about? That should be the impedance right there. You have a question? Just ask. I want the voltage here, right? So the impedance of that element is this, divided by, that's this, divided by the sum of the two impedances, those two. You see it? Okay, guys?
And then you're multiplying top and bottom by j.
Yeah, because I want to get it in a form that's more manageable. So if I multiply top and bottom by j n omega naught c, I get 1, right? Then I get j n omega naught c r here, and I get 1 on top. Got me? Now, that has a magnitude and an angle. You got to get this. So the magnitude would be 1 over the square root of 1 plus, and then you have to take n omega naught times r times c and square it, right? That's the magnitude. Do you agree with me? Because we have an imaginary number, real and imaginary. You square the imaginary's value, plus square the real value, take the square root to get the actual it's really like the hypotenuse of a triangle, correct, class? Now I need the phase angle. Well, what's the phase angle of, I have to do this, I do this at least once every time. If I have a plus jb, do you all realize that it's equal to a squared plus b squared? That's the magnitude. And the angle is what? Tan minus 1 of opposite b over a, isn't it? Y'all know what I'm talking about, right? Opposite over adjacent is tangent, inverse tan gives me the angle, correct, class? So when I do this, well, the phase angle of this is what? It's just tan to the minus 1 of n, opposite n omega naught r times c over 1, correct? Correct, class? What happens when I take 1 over the angle? If I have 1 over 1 at an angle of 30 degrees, and it's really 1 at an angle of minus 30, isn't it? When I go from here to here, the phase angle flips. So this is really going to have an angle here of minus the tangent of minus 1 of n omega naught r times c. So we have a transfer, yeah.
Is it because that angle is originally in the denominator?
Yeah, that's
Okay.
exactly why. And just think about this. Suppose I have 1 over 1 at an angle of 30 degrees. Isn't that really 1 at an angle of minus 30 degrees? Everybody see that? So come over here. Now this is my transfer function the way I need it. Magnitude and phase. Got me? That's how I get the phase. And that's a question that will come up repeatedly. People say, how do I get the phase of this? It's always find the real, find the imaginary. Take the imaginary divided by the real. Take the inverse tangent of that. That's the phase angle. That's the way you do it. There's no magic here. Now, we've got the transfer function. We've got the Fourier series, right? We've got the circuit. Now we're going to get the output, right? Yes, sir.
You're squaring this and then taking the square root to get the magnitude?
Yeah.
Okay.
That's what you have to do. If you think about A, B, right? We want this. Square this term, take square root. It's really like a triangle thing. Right triangle. Y'all see this? Now hang with me on this one. So now I'm going to put it all together for the output. Now I'll tell you what the real bugaboo in this is in MATLAB you have to be careful with the dot times, and I'll spend some time on it. It'll drive you nuts if you don't. If I had more time today, I'd pull up MATLAB on that thing and I'd show you what I mean by the problems you can run into.
Are we still doing that Wednesday?
Yeah, are we supposed to bring in our laptops?
Why don't we? Yeah, I think that would be perfect, because I'm right at the point where I need you. Do you all have laptops here? Anybody, does anybody not have a laptop? Can y'all bring them in for me on Wednesday? Because if you can bring them out on Wednesday, then I can go through and systematically show you how to do stuff with MATLAB. Have you running it? If you run into a problem, somebody can go help you or I'll help you. And that way we'll take care of a lot of questions all at once. Got me? All right, I mean, y'all have you need MATLAB though.
We can
You can get
virtual.
it.
What?
Use virtual labs.
Can you, all right, if you're in here, bring your laptop, can you show these people how to do the thing? Because I've got MATLAB and I don't have the virtual MATLAB. Some of you may like Python too. Python will do this too. It's free. And if you want, there's a free version of MATLAB called Octave. Has anybody used Octave? It's slower, but it'll do the same thing, virtually the same code. In some ways that's better. Octave might be better because you don't have to worry about FlexLM licenses and some of the other things that irritate me, like firewalls. You can't get a FlexLM through. All right, now, when we take a look at this, my y of t, please pay attention. First, I'm going to take x0, whatever it is. It's the value of a function. In my case, it was what? I erased most of that, but in my case, it was, it's a tau, right? A times tau divided by 2t, right? That was, you had to divide by capital T, right? It's the area divided by the period, correct, class? It's that times the transfer function at 0. That was a capacitor in series with a resistor. That is a low-pass filter. All of it passes, so it's just times 1. I know the transfer function, right? The transfer function we had was this. Was equal to 1 over 1 plus j n omega naught times r times c, right? Well, when n is 0, that's the first one, you get 1 over 1 is 1. Now you have to do this, plus the summation, bear with me, n equals 1 to infinity. When you do this, you take up maybe 100 terms. Now I put in the coefficient. First I'm going to put in 2 times the magnitude of c of n. Well, what was the magnitude of c of n? It was what?
1 over square root of 1 plus n omega naught times c2.
No, for c of n. Was it?
It was, let's see, a times e to the negative jn omega naught tau over 2
All right, that doesn't matter, that's a phase.
over t times n omega naught j,
That's right.
and then multiplied, the whole
by
term
sine.
multiplied by a sine, 2j sine
No. There's a sine
n omega naught tau over 2.
tau over 2 here, and then there's a 2j, right?
Mm-hmm.
All right, now, we want the magnitude, so I'm just going to mention this. Please just watch this. The magnitude phase doesn't matter. Do you all see that? I can leave that there. I can erase that phase. The j doesn't matter here. The j doesn't matter here. Actually, they cancel. So I get that. Another cleanup I can do is what? Omega naught is 2 pi over t times t. Just take this whole thing and make it 2 pi n. Here, that's phase. I don't care about the phase. I'll leave a in there. And I got a 2. Well, the 2's cancel there, so that's my coefficient for c of n, magnitude-wise, right? Now, what's the magnitude of this? Just magnitude. Well, that's simply times 1 over the square root of 1 plus n omega naught times r times c squared, right? You gotta take the square. That's c of n, h of n, magnitude, correct? Now you put in the cosine of n omega naught t plus the phase angle of this term, right? And the phase angle of this term was what? The j's canceled, but you had that e to the j, e to the minus j n omega naught tau over 2. Let me just say this. There's a term e to the minus j n omega naught tau divided by 2 that's multiplying this stuff. That has a phase of this angle, right there. So what you put in here is plus or minus in this case, n omega naught tau over 2. That is the phase. Do y'all follow me on this? That is the phase, period. All right, and you can put omega naught here as 2 pi over t if you want, and then it's tau over t as a ratio, it's the actual duty cycle. Now what's the phase of this? Of this? It was minus the tangent, right? It's minus the tangent, minus 1 of, then it's going to be just n omega naught r times c. And believe it or not, that is the output. Y'all follow me on this, class? Now, this may look like, oh, it's tough to do. Remember the one I gave you, the MATLAB project I gave you? I gave you the basic skeleton code. You had to just change C of n, right? I had all the stuff here. Here, it's basically the same thing. Now, the C of n that you used is just going to be this. Y'all see that? It's no longer just a series, it's 2 series, right? It's h of n times x of n. Okay? It goes in there. I want to tell you one thing. When you do this in MATLAB, anytime you do MATLAB multiplication, if you have A asterisk B, this is a multiplier, that means that these components have to have the same size. If this is a 2 by 2, I mean not same size, but they have to agree. For instance, if you have a 2 by 2 matrix crossed in or multiplied with a matrix over here, it could be a 2 by 3 and the results would be 2 by 3. But you can't have a 1 by 3. Then you'll get matrix disagreement. But if you want to circumvent that, now you put a dot there. And a dot means it's term by term multiplication. I'm out of time, I'm over actually. I'll spend more time on that on Wednesday. Please bring in your,
Can you pick it up and have that one?
I picked it up, didn't I?
Yeah, you did on Friday.
Yeah, I picked it up on Friday. Is that the one you're talking about?
I don't know, I looked at one 14th, and there's one that was.
That was the one due Friday, correct?
Yes.
Yeah. Did you have it? Bring it up.